Welcome, everyone. My name is Samantha Sanderson, and I am a current undergraduate at Southern New Hampshire University, where I am majoring in environmental science with a concentration in conservation and natural resources. Today, I want to shed light on a growing environmental crisis, groundwater overextraction, and its devastating impact on aquifer depletion and land subsidence. In agriculture regions where irrigation is essential, the excessive withdrawal of groundwater has led to severe consequences. Using cutting-edge satellite technology like GRACE and INSAR, we have analyzed how long-term groundwater extraction causes land to sink, threatening infrastructure and increasing flood risk. With climate change worsening precipitation patterns and reducing groundwater recharge, urgent action is needed. This research highlights the necessity of sustainable water management, advanced hydrological monitoring, and policy interventions to mitigate further damage. Now let's dive into the details. Now I want to start off with a short introduction. Groundwater is a lifeline for millions. We all know this, especially in arid and semi-arid regions where surface water is scarce. But what happens when we take more than nature can replenish? The result is aquifer depletion, leading to land subsidence, where the ground physically sinks due to a lack of underground support. This isn't a distant concern. It's happening now, impacting water security, agriculture, and infrastructure. Understanding this process is crucial to preventing long-term environmental and economic consequences. Now, groundwater overextraction is a recognized global crisis. Studies have shown that without intervention, many aquifers may face irreversible depletion. Research by WADA in 2010 emphasized that agriculture is a primary driver of groundwater depletion. Figmigatti in 2014 reinforced this, linking excessive withdrawal to land subsidence, particularly in California's Central Valley, where sinking land has caused infrastructure damage. Other studies, such as those by Perkins and WADA in the year 2019, highlight how climate change exacerbates groundwater loss, while research done by Ritchie in 2015 utilized GRACE satellite data to identify critical depletion zones in northern India and the United States. Collectively, these findings stress the urgency of sustainable groundwater management and the need for regional specific policies. Now, we all know with good research, you have to conduct a good hypothesis. Based on this research, my hypothesis is clear. If groundwater overextraction continues in agricultural regions, land subsidence will significantly increase over the next 10 years, leading to infrastructure damage, higher flood risk, and reduced water availability, which is kind of important. This decline in groundwater levels will not only disrupt ecosystems but will also place additional stress on water resources that millions rely on for drinking and agriculture. Furthermore, regions with poorly regulated groundwater policies will experience more severe consequences, exacerbating economic and environmental instability. Now, by analyzing the relationship between extraction rates and subsidence patterns, these studies aim to demonstrate the urgent need for sustainable water management practices to prevent irreversible damage to aquifers and the landscapes they support. To analyze this issue, we used a combination of satellite data, ground-based measurements, and hydrological models to assess groundwater depletion over a 10-year period. GRACE satellite data allowed us to track long-term groundwater storage changes in agricultural regions, identifying depletion zones, while INSAR technology, as seen in the first image, was crucial in measuring land subsidence over time, helping us pinpoint areas affected by excessive water extraction. When we used our ground-based monitoring, we utilized well data and extraction records to validate satellite findings and assess localized impacts. Geospatial mapping was employed to visualize depletion patterns, helping to identify hotspots of rapid water loss. Remote sensing analysis integrated various satellite datasets to compare historical and current trends in groundwater depletion. The analysis also included correlation studies, comparing groundwater depletion rates with subsidence levels and predictive modeling to forecast future depletion trends. Additionally, comparative case studies between regions with different water management policies provided insights into how regulations impact depletion rates. This multi-scale approach gives us a clear picture of the ongoing crisis and what lies ahead. With that being said, this brings me to my next section, results. Our findings confirm a strong correlation between groundwater depletion and land subsidence, particularly in heavily irrigated agriculture areas. Gray satellite data revealed drastic declines in groundwater storage in places like California's Central Valley and northern India regions already experiencing severe water stress. INSAR technology, as demonstrated in the images, visually confirms land subsidence, showing how excessive extraction has physically reshaped the landscape. The images of California from 2002 to 2014 highlight just how dramatically groundwater depletion has worsened over time, with the color shift from green to deep red representing severe loss. A similar trend can be seen in northern India, where equivalent height anomalies in groundwater storage emphasize widespread depletion. These findings indicate that without intervention, continued overextraction could lead to irreversible aquifer depletion worsened by climate change. Land subsidence will further damage infrastructure, increase cost, and raise flood risk, making groundwater management more critical than ever. Ending with our conclusion. This research underscores the urgent need for sustainable groundwater management and proactive conservation efforts. The data shows that if unsustainable extraction continues, aquifers will suffer long-term depletion, leading to environmental and economic consequences that may be impossible to reverse. Climate change further complicates the issue, making groundwater loss an even more pressing concern. To address these challenges, governments, environmental agencies, and industries must collaborate on sustainable solutions. Implementing more efficient irrigation techniques, enforcing stricter water regulations, and investing in advanced hydrological monitoring systems can significantly slow the depletion rate. Additionally, public awareness campaigns and incentives for water conservation must be strengthened to encourage responsible groundwater use at all levels. If no action is taken, the consequences will extend far beyond regional water shortages. Agriculture will suffer, ecosystems will deteriorate, and economic losses will mount. However, by leveraging the knowledge gained through research and satellite technology, we can make data-driven decisions that prevent further damage. Sustainable management isn't just an environmental priority. It is a necessity for ensuring long-term stability and resilience against climate change. Ultimately, our ability to protect groundwater today will determine the livelihood of future generations. As a society, we must act swiftly and decisively to safeguard this vital resource. Now, as with all research, our findings are built upon the contributions of leading scientists in the field. Studies by Perkins and Wada in 2019, Famiglietti in 2014, and Ritchie in 2015 provided invaluable insights into groundwater depletion, climate impacts, and hydrological trends. These resources reinforce the importance of continued research and policy development in water resource management. Now, before moving on to my closing statement, I would like to acknowledge and extend my gratitude to Southern New Hampshire University for providing the resources that made this research possible. And a special thanks to Professor Caldwell for her guidance and expertise throughout this project. Additionally, I recognize the contributions of NASA's GRACE mission, INSAR's satellite data and hydrological models, which played a critical role in understanding the scope of this issue. I want to end this presentation with a closing statement. Groundwater depletion is not just an issue for the future. It is happening now. If we fail to act, the consequences will be severe, affecting agriculture, infrastructure, and water security for millions. And I know throughout this whole presentation, I have repeated those: agriculture, infrastructure, and water security. But that is how serious this issue is. And those three things are so valuable to this planet that it needs to be brought up, and we need to make a difference. And by implementing these better policies, utilizing advanced monitoring systems, and promoting sustainable water use, we can mitigate the damage and preserve groundwater for future generations. I thank you for your time, and I welcome any and all questions.